There's another type of equilibrium problem that you cannot get all the information from the question itself and solve for k. In this case, they give you k and ask you to kind of solve for all the equilibrium concentrations. Let's see how this one's a little different. So here we have our reaction. Some very similar information. 0.5 moles. This one's in a 2-liter container, so we need to do some division to get the concentrations. This is a 0.25 molar solution. Let's make this a little bit bigger. And a 0.86 moles of oxygen, so 0.86 over 2 gives me 0.43 molarity. Those are all molarities in a 2-liter container, assuming there is no product there. So initials still look good. The change we always have minus x, and this one is going to be plus 2x because of the coefficient for the NO. What are the equilibrium concentrations of everything? Well, we don't know. We know they're not going to go to 0. We know that this one is going to be 2x. This one is 0.43 minus x, and the nitrogen is 0.25 minus x. Okay. Now here we have our k expression, our k constant. K is still going to be, the expression is NO squared over N2 times O2. Now, this is a case where we have K. K is 4.1 times 10 to the negative 4th, okay, which we know is going to favor the reactants. But we still need to figure out these amounts. NO, if we just plug in here, there's really only one variable here that's missing, and it's x. NO squared, so 2x squared. And then in the denominator, you can see where we're going with this. 0.25 minus x, that's my nitrogen, times 0.43 minus x, that's the oxygen. We have a complex algebra equation. To solve for that, you are allowed to use your calculators, and you will get your x value equal to 0.0033. So what are the concentrations of everything at equilibrium? Well, my nitrogen is 0.25 minus x. Well, that's still going to be 0.25. So you'll notice that one didn't really change. The oxygen doesn't really change either. It's 0.43 minus x, and that x value is too small to register for the change of those reactants. So still going to be 0.43 molarity. And then the NO, that one it was 0, so that one's definitely going to change, is 2x, which is going to give me 0.0066 molarity. Okay, so we have equilibrium concentrations of everything here, but we had to use our K expression and a little bit of algebra, and if you use the solver on your calculator to solve for that. But what I want to do is I want to show you, there's another way you can do this. If you're in a pinch, and this doesn't work all the time, I'll show you another example here where this doesn't work. But if you do not have a calculator, you'll notice that this K value is very, very small. It favors the reactants. And a lot of Ks are like that when you have equilibrium. And you'll notice that our reactants did not change. Okay, so your book will talk about some rules and some assumptions that you can make, and if you have your calculator, I would always solve it like we did here on the screen. But if you don't have your calculator, the alternative is to look at this another way, and we say 4.1 times 10 to the negative 4th equals 2x squared, okay, just like we did before, so 4x squared when you expand that over. Now, if we know that this is so small, these x's aren't, going to change these initial values? We can just use this and say, oh, 0.25. This initial value may not change. There are a lot of times where those x values are insignificant for your reactants. Now this is much easier to solve. Not the cleanest numbers in the world without a calculator, but it's much easier to solve than trying to do a quadratic with your calculator for this one. So this one would only be done in an emergency, and the conditions here are for a very small k. That's the only way that the x's are insignificant, when you have a very, very small k value. Because when that happens, then your initial concentrations of your reactants don't change. Okay, here's another one, and this one you're not allowed to do that method, because we look here and we say this is k is 1.2 times 10 to the negative second. That's not a very small value. It's small, but it's not going to be big enough to assume that the x's don't matter. So watch what happens with this one. H2, let's get the black pen back out. H2SO3 turns into H plus and HSO3 minus. We have 1.5 molar initially, and none of those. We know that this is going to decrease by x. Those are going to increase by x, so we get x and then 1.50 minus x. Okay. The k expression here, let's kind of keep sliding this up. And we have 1.2 times 10 to the negative second equals my hydrogen times my hydrogen sulfite, which is also x, over my reactants, and all the coefficients are 1.50 minus x. Now if you just assume that this x doesn't matter and try to put it in your calculator a little bit easier, then you're going to get the wrong answer. This one you're going to need the solver, you're going to need the quadratic, and to distribute and rearrange everything. Your x value here is going to come out to be 0.128. Okay. So watch what happens. My hydrogen concentration is x. It is equal to the HSO3. Because the question is, what's the concentration of everything? So 0.128 molar. But when I do 1.5 minus x, 1.5 minus x, then my H2SO3 is actually different. It's going to be 1.37 molar. Okay, so that changes things because that x is significant. If you assume that the x is insignificant when you're not allowed to, you should always double check. Put it in this and see if it changes that. Sig fig wise, if it doesn't change it, you're okay, but if it changes it, you probably did something wrong. This is a larger value of x. You just need to put it in your calculation.